Hi, this sample problem video is to help out with advanced chemical conversions, specifically those involving density and molarity. Now, the first question we're going to look at asks how many gold atoms are there in 517 milliliters of pure gold if its density is 19.32 grams per milliliter. Now, the first step is we got to figure out what our starting point is and what our end point is. So the fact that it's asking how many gold atoms, that is our end point. How many atoms of gold? Now, our starting point, we have two numbers given, here or here. Now, since I know that density is in fact not an island on the chemical conversion chart, but density is, in fact, a double-headed arrow, so a bridge. I know that that cannot be a starting point. Instead, the volume of a pure substance, in this case gold, in milliliters, is. So that means that my starting point is 517 milliliters of gold. Okay? Now, from there, we need to figure out what our equalities are. Again, looking back on the chart, my starting point is here in the volume of a pure substance in milliliters. The end point is over here on particles, because that's where atoms live. And it looks like we're going to be jumping once, twice, 3 times. So we need 3 equalities. We need the density, we need the molar mass of the substance, and finally we need Avogadro's constant. So the first equality is density, and it's right here. Now, to change that into an equality, it says that there are 19.32 grams of gold for every 1 milliliter of gold. Remember, you just make 1 for whatever's on the bottom of a compound unit like that. So we have 19.32 grams of gold equal to 1 milliliter of gold. Now we need the molar mass of gold. Now the molar mass of gold, according to my periodic table, is 196.97. So there's 196.97 grams of gold for every 1 mole of gold. Remember, molar mass is the mass in grams equal to 1 mole of a substance. And then finally, we need Avogadro's constant, which is always 6.022 times 10 to the 23rd particles, in this case, atoms of gold, for every 1 mole of gold. Now that we have our equalities, we take our starting point, and we want that to be in the top left-hand cell. So we have 517 milliliters of gold. Here's our starting point. Now we have milliliters of gold. We want milliliters of gold on the bottom. They're right there. It's only one amongst our equalities. So I put 1 milliliter of gold, and that's equal to 19.32 grams of gold. Once I use an equality, I cross it out, don't use it again. Now I have grams of gold. I want grams of gold down there. So the only other grams of gold is right there. It's 196.97 grams of gold, and it's equal to 1 mole of gold. I've used that. Now I'm done with that. And finally, I have moles of gold. I want moles of gold down there. Only other mole of gold is right there. So 1 mole of AU is equal to 6.022 times 10 to the 23rd atoms of AU. So once we have that, we double check to make sure all of our units cancel out. So milliliters of AU, milliliters of AU. Grams of gold, grams of gold. Moles of gold cancels out with moles of gold. Only thing that doesn't is atoms of gold, and that's right where we want to end up. So now on my calculator, if it's on top, I multiply. If it's on the bottom, I divide. So that's show you here. That's 517 times 19.32 divided by 196.97 times 6.022 EE 23, or times 10 to the 23rd, equals. So on my calculator, we have 3 significant figures in our starting point. So I rounded off after the 3rd digit. I have 3.05 times 10 to the 25th atoms of gold. And that is my answer to my first problem. Now, the second problem deals with molarity. Now, this question is asking how many grams of a hydrogen nitrate are required to make 5 liters of a 3.5 molar nitric acid solution. Well, the first step is, if you notice, nowhere on here does it give us the formula of this substance. We got to figure that out. Either we can use hydrogen nitrate or the fact that it's nitric acid. Going nitric acid, since it's ic acid, I know the original anion ending was 8, so that means it was nitrate. On the back of my periodic table, I look for nitrate, and I see it right here, nitrate, and it has a formula of NO3, -1. NO3, and since it's -1, I only have 1 hydrogen in front, and I put AQ when it's dealing with a solution. So now I can have my starting point. Again, molarity is not an island. Instead, molarity is an equality. So I know that can't be my starting point. All right? It says volume of a solution in liters. Well, I have 5 liters of a solution, so that's going to be my starting point. 5.0 liters of nitric acid, okay, solution is my starting point. And the end point is it's asking how many grams of hydrogen nitrate. So unknown number of grams of HNO3 are going to be required for that. So my starting point is over here on volume of a solution in liters. My end point is over here in mass in grams. I'm doing 2 jumps, so I need both the molarity as well as the molar mass of hydrogen nitrate. Now the molarity is 3.5 molar solution. Now when it says molar, remember, molar is the same thing as moles per liter, which means that I have 3.5 moles of hydrogen nitrate for every 1 liter of nitric acid solution. So that I got this from this, okay? Now the second equality I need is the molar mass. Now I have 3 oxygens at 16 each, so that's 48. 1 nitrogen at 14.01, so that's 162, that's 62.01. Then I have hydrogen at 1.01, which gives me 63.02 grams of hydrogen nitrate for every 1 mole of hydrogen nitrate. Now that I have my equalities, I set up my grid. I have 5.0 liters of hydrogen nitrate solution, i.e. nitric acid. And now for every, I have liters of nitric acid, I want liters of nitric acid down here. So that's right here. That's for every 1 liter of nitric acid solution, it is equal to 3.5 moles of hydrogen nitrate. All right, so I've used that equality. I won't use it again. Now I have moles of nitric acid. I want moles of hydrogen nitrate on the bottom, and they're right there. So 1 mole of hydrogen nitrate is equal to 63.02 grams of hydrogen nitrate. Liters cancels with liters, moles with moles, and I'm left with grams of hydrogen nitrate, which is exactly where I want to end up. On my calculator, if it's on top, I multiply, bottom I divide. So that's 5 times 3.5 times 63.02 equals, now that's greater than 1,000, so I'm going to want to put that in scientific notation. So that's, there's 2 significant figures in the starting point, so I need 2 significant figures in the end point. So that's 1.1 times 10 to the third, and the units are grams of NO3. And there's my answer. I hope you found this useful. Good luck.